On May 25th, 2008, a powerful, often overlooked EF5 tornado struck Parkersburg and New Hartford, Iowa, carving a 40-plus mile path through mostly rural farmland, but producing EF4, EF5 damage along the way on the south side of Parkersburg and into New Hartford. I am Gabriel Harbor, and you are listening to the Storm Chaser Coaching Podcast. Before we dive into the questions today with Coach Trey Greenwood, there's a link in the description where you can get the cheat sheet for this episode. Cheat sheets contain all of the notes we use to build out each podcast episode. And if you click that link one time, you'll unlock access to the cheat sheets for every single episode we ever have or ever will record. Okay, Trey, let's go ahead and get into it. How did the secondary surface low in that weird north-south warm front set the stage for such a long-lived EF5 tornado?
This was a really unique case, especially with the surface features. You had a surface low up in northwest Minnesota, cold front stretching down to a secondary surface low in the northern Iowa, southern Minnesota vicinity. Then from that to the southwest, you had your cold front, but to the southeast of that, you had a warm front that was draped basically almost north-south, which is quite unusual. Your typical schematic of a mid-latitude cyclone or surface low has your cold front down to the south, warm front off to the east. That was not the case in this scenario. The warm front was actually draped much more north-south. So you'd think with more east or northeast moving storms that they would be easily crossing that boundary into the cooler air, which was not favorable for tornadic activity. But the warm front was actually slowly shifting east with the actual storms as they developed. So those storms were able to remain in that warm frontal zone or near that warm frontal zone for a long duration as they moved in concert with one another. That allowed them to remain significantly tornadic for quite a long period.
Just a couple of patterns I'm starting to notice as I get these opportunities to talk with you more about severe weather. It seems like, number one, whenever the larger scale features are moving along with the storms, it really provides an opportunity for some explosive things to happen. And then number two, I think you mentioned the orientation of the warm front. It seems like whenever there are these very strange setups, modeling out how you think it's going to go just doesn't always work out that way because it is so novel that there are just so many factors that can come into play to change up what you think you know.
Yeah, I can't really recall a specific analog to this case where you had almost a due north-south oriented warm front like this. Obviously, as we said, that's usually not good. Any type of boundary that's oriented more perpendicular to storm motion is going to be unfavorable for those storms remaining near that boundary. And they tend to cross it pretty quickly and become elevated or non-tornadic. That just wasn't the case here, even though you had a north-south warm front. So this was very unique. And this was, if you just did a quick glance at the surface obs, you probably wouldn't see this. You had to do some detailed analysis to actually pick this out. It goes to show that it requires a very astute look and detailed look at the surface observations and all of your products before you actually select a target and adjust from there.
Now, if you're a forecaster who's watching this situation in real time, you see a supercell anchoring to a warm front, what should you be looking for at that point? And obviously, Storm Chaser is implied here as well, but just what is the overall thing that should take over in your mind when you see a situation like this?
So when you see a storm anchoring, that's usually going to involve a pretty distinct change in character. The storm might be relatively outflow dominant or just not all that impressive. It might certainly be a supercell, but it might not have very strong low-level rotation, and it just may be a little bit disorganized. When you see that latch onto the boundary, you'll see a pretty distinct change in character toward more of a stronger low-level mesocyclone and oftentimes more of a tornadic look to it. And once it latches, it can produce tornadoes for quite some time. You'll see a very quick change in character, oftentimes visually as well as on tools like radar, and even on satellite, it might explode in some of those cloud tops. So overall, the storm will start to intensify in a rapid fashion in most cases once it anchors to the boundary.
There are so many things to talk about with each unique storm situation, and if you want to be where the discussion is happening, pound for pound, in my estimation, the best community for severe weather that exists is the Storm Chaser Coaching Discord server. So that link is in the description below. Highly recommend you join, talk with our members, talk with our coaches. It's a great time. Trey, next question. From a radar perspective, how do features like a descending reflectivity core change your confidence that a supercell is about to produce or intensify a tornado? And I'm pretty excited to hear the answer to this one because this is even well outside of my realm of understanding.
Yeah, this is actually something that there's research being done right now on this by people like Chris Broyles. They're looking into a lot of these strong to violent tornado cases, and they're finding a lot of these descending reflectivity cores are in place and actually occur immediately preceding tornado genesis, and the Parkersburg case was no different. You have to kind of look on 3D radar, so it's not something you might often see in real time. You can see it on 2D radar in reflectivity sometimes, but it can be a little bit tricky. But if you have a 3D radar picture, you can often see a little core, a little blob of stronger precipitation and stronger flow descending down into usually the region near the hook echo. Sometimes this will occur well before tornado genesis, and it actually may signify the beginnings or intensification of the hook echo. It becomes a little bit better defined. But immediately preceding tornado genesis, that is something that we've seen is pretty much critical. We're seeing a lot of these violent tornado cases have these DRCs or descending reflectivity cores with them. So if you are able to pick out a descending reflectivity core in 3D radar or you see it on 2D radar, again, it can be pretty subtle. But if you see an increase in reflectivity near the hook in a little bit of a localized area, or if you have 3D radar up and you see a little bit of a blob of precipitation descending near the hook echo, that can be a sign that you're about to undergo tornado genesis or that a tornado is going to intensify.
I love how many little things like that are still left to be studied and discovered in meteorology. It is by no means a settled science, and I think that's one of the more exciting things about forecasting and storm chasing.
Yeah, we still don't really have the complete answer as to why certain storms produce tornadoes and others don't in very similar environments. And these small things are starting to enlighten reasons why one storm might produce while a neighboring one might not. These small things like descending reflectivity cores and other storm scale interactions, stuff like that. It's making the science really interesting. And we're getting closer to that, to answering that question of why some produce tornadoes and why some storms don't.
Now, Trey, I went a little out of order because this next question I actually have on the list from earlier. So I hope I'm not throwing you a curveball or I'm not too far out of the timeline here. These are old notes actually from the new format that we're using currently. But can you explain how the gravity waves, especially that trailing one that you mentioned in your Convective Chronicles YouTube video, how did that likely influence mesocyclone strength and tornado genesis for the Parkersburg storm?
This was a really unique situation where you had oftentimes we talk about gravity waves being induced by actual strong convection. You can think of it as throwing a rock into a calm pond. If you throw it into a calm pond, it's going to create ripples outward from the source where the rock goes in. Same thing in the atmosphere. If a strong storm or storm complex goes up in the atmosphere, that can sometimes not mess up, but in that same vein, it allows energy to radiate outward from where that's happening, and you can get gravity waves. In this case, we didn't have any preceding convection, but what we did have was a synoptic pattern that was favorable for non-convective gravity waves. You had a very strongly diffluent flow in the exit region of the shortwave I talked about in the Convective Chronicles video. Diffluent means the flow is just spreading apart in the upper levels of the atmosphere. When that happens and you have a strong capping inversion in the low levels, which we had in place on the Parkersburg day, that can actually allow for gravity wave development and propagation. And if you look at satellite imagery, it looks like you can track some of these gravity waves going east and actually impacting the area where the Parkersburg storm was as it was intensifying. We saw one, including using some radar data, that one of these gravity waves went right over top the Parkersburg storm, immediately preceding significant tornado genesis and into that very significant EF5. So what this research has shown that these gravity waves, and this is somewhat of a rare situation, but when this happens, these gravity waves can actually generate horizontal streamwise vorticity, which is very favorable for tornado genesis and supercells in the inflow region of the storm. And then the updraft kind of tilts and stretches that into the vertical. And that can really bolster the chances for tornado genesis when you have that in place. So this was a really fascinating case where these gravity waves appeared to play a significant role in the intensification of the storm.
I guess they don't call it chaos theory for nothing, huh?
Yeah, these cases are so interesting where you have some of these outside factors just completely throwing a wrench into things.
Last question here that we'll close on. Given the strong low level shear, but somewhat weaker mid level shear, how did that combination help the tornado stay on the ground for over an hour?
Yeah, the wind profile near the Parkersburg storm had some similarities to the quote unquote forever meso hodograph that has been espoused by people like Cameron Nixon. It wasn't a full forever meso hodograph, but it did have some of the characteristics, like you said, strong low level shear, weaker mid-level shear. This is something we often see in the southeast for those high-end, long-track tornadic supercells out there. And the Parkersburg storm had some of the same similarities in the wind profile. Oftentimes, these storms are fairly compact. Parkersburg storm was a little bit bigger because we had very strong storm relative inflow going into the storm, which modulates how much mass is going into the storm, and therefore we got a larger storm out of this. But usually these consist mostly of a very large tornado cyclone, which allows them to produce in a steady state these tornadoes for a very long period of time without interruption. So this was not quite the same thing as a typical forever meso type case, but it certainly had some of the hallmarks of it. That's why we got a very long track tornado out of this.
Remember to check out those links in the description below, and then watch another video.